Good morning, my fabulous chemistry faithful. Video number 6, we're going to get into branches, or what I would call side chains. What happens when we have a side chain on a straight chain. So these branches are just some number of carbons attached to the parent chain. You can see down in the picture we have a few different guys going on. And you can see if you look carefully at the naming structure, we'll have a little bit of a new variation in the naming structure. All right, the parent chain or the backbone is the longest straight chain of carbons. So we would start counting with our pencil or pen like on the paper, and the longest chain without having to actually pick up your pen or pencil is going to be the backbone, even if it's bent, which would be the middle picture. I could show you that the longest chain is the 3 going up and down and then go over 2. That would be 6. If I just counted across the bottom, it would be 4. So I can get 6 if I count going up. So that's actually not the parent or the side chain going up. Okay. Multiple bonds in the parent chain win, so they trump. If there is a double bond in the parent chain, that's the parent chain, period. So let's say there's 6 carbons this way, and then there's 6 carbons this way. Well, if I count flat and that has the double bond, then that's the parent chain. So if there is a double bond or triple bond present, that has to be in the parent chain. Okay. And then we got some nomenclature. So how do we name these things? So some things are going to start off the same, and this video is going to go painfully through these pieces like the other videos, just so we never lose these skills. Prefix first tells me how many carbons. I need to know how many carbons in the parent chain. And then the root tells me the kind of bonding, again, in the parent chain. And then I'm going to name the side chain similar to the parent chain, except for I'm going to remove the ane and replace with an ill, and you'll see this. So these guys are going to have 2 names, and the number of carbons in the parent chain go with the same rules as the prefix and the carbons in the, I'm sorry, I misspoke. The number of carbons in the side chain get named the same way the parent chain's carbons get named. If there's 1 carbon, it's meth. If there's 2 carbons, it's F. If it happens to be a 3 carbon chains, it would be a prop. The thing that's different is I take the ane off of the methane and make it a YL, so it would become a methyl. Once I see that YL, I know it's a side chain. And I don't know, maybe you can think of that Y as having a side, looking like a side chain. I mean, that's how you remember it. Okay, but we do it enough times and we'll just get it. And then again, the number tells us where either the multiple bond is in the main chain or where the side chain is. And we're going to do multiple examples so you can see that there's 2 numbers, 1 number in front of the side chain to tell me where the methyl is, and then another number directly in front of the parent chain to tell me where the double bond or the triple bond is. And the number, obviously, it's going to be, if it says like 2 methyl, the 2 is applying to the methyl. And if it says 2 methyl, 3 propene, or something like that, then or not propene, but like 3 pentene, the 3 is where the double bond is on the pen. So we'll go through this ad nauseum to make sure we all got it. The examples cover the spectrum of what we need to know. And then the lowest number wins rule still accounts for this too. So I have to count from both directions to make sure I get the lowest numbers possible. So let's get into this. There are 6 of these, 8 of these examples. So it's going to take me a few minutes to get through them, but I want to go through them ad nauseum to give you some examples of how we do this. The third example here might be one of the most complicated of them. Okay, so I'm going to pull out the bute out of 2-methyl butane. I see that YL, so I instantly know there's a side chain. My parent chain is the butane piece. So bute, we know ad nauseum, bute is 4 carbons. So I'm going to put 4 carbons. And then I know that the ane tells me that they are all single bonded. But ad nauseum, still got the graphics rolling, make sure we understand what's up. So I know it's 4 carbons single bonded as my parent chain. And then I had this methyl to deal with. Well, meth is 1 carbon, and the YL tells me it's a side chain. Okay, so I have a 1 carbon side chain. Well, where am I going to put it? Put it on the 2nd carbon, and it goes there. There's my methyl. I'm basically done. I just have to fill in my H's, and this is 2-methylbutane. Now, this is a great example. If I had pen and paper or I had the ability to draw on the smartboard at school, I would show you that if you count across the bottom, you got 4. If you start at the top and count down, you got 4. If you start at the top and go the other direction, you only get 3. So 4 is the longest number in a row I can have. That's where I get the but from. Okay, and then molecular formulas, just count them all up. So it's C5H12. Carbons are all single bonded, so it is saturated. Okay, this is another great example. When I count, counting straight across is 5. If I count around the bend, I get 5. If I count from the bottom of the bend and up and over either direction, I still just get 5. So I can't get a longer side chain than 5 on this. Or I'm sorry, a larger parent chain. Man, I gotta really slow down, Milks, but these videos take so long. I want to get through them for you too. So 5 is the longest side chain I can make. I default the longest main chain, the longest carbon backbone I can make. Parent chain. Ugh. The parent chain is going to be 5. If you can keep it in a straight line, do that. I mean, it makes sense to keep it in the straight line. It doesn't make any sense to bend it. We will get at some point into some of the practice where a side chain cannot be at the end carbon, by the way. Okay. If it's at the end carbon, then that's still just a straight chain. It's just bent. So I don't think I've said that yet, but this is where that comes into play. And it does upset some kids. If I took those 2 carbons that are on the bottom and I just slid them over to the end, well, then it would be a 7 carbon straight chain because I could count them without picking up my pencil. Okay. Bonding between my carbons is all single, so therefore it ends in ane. So it's a pentane on my parent chain. So now I have to deal with these 2 carbons because we just identified those 5 carbons going across as the pentane. So now this is my side chain. So 2 carbons on a side chain is 2 carbons F. Side chain ends in -il, so it's ethyl pentane. Now, where on earth is this ethyl group? It is on the 3rd carbon. So 3-ethyl pentane. If we were in class, and what I can do in class is show you that there's no such thing as 2-ethyl pentane. So somebody remind me that if I move this over, we'll see that I actually can make a 6 carbon chain now. Okay, so it wouldn't be a pentane anymore, it'd be a hexane with a methyl. So if that's confusing to you, I want to make sure we do that in class so you can understand that. So somebody bring that up and remind me, okay? Again, there's count them all up, and then it's saturated, all single bonds moving along. This guy's got 2 methyls, so this is going to be complicated. However I count this, I come up with 5. 5 is the longest chain I can make, so it's instantly a pent. Single bonded, it's an 8. Okay, I'm going to try and move this along a little faster. So I got pentane going across the middle. Now here are then my 2 side chains. Makes sense. Each side chain is 1 carbon long. So 1 carbon is a meth. Okay, so boom. But here I got 2 of them. So to say I have 2 methyl groups, we say dimethyl. Dimethyl, 2 methyls on a 5 carbon single bonded main chain. That's what I see there in those words. 2 methyls, dimethyl, so 2 1 carbon chains on a pentane, which is a 5 carbon chain single bonded. Okay, decoding the words. Now I have to give you an address. So if I count from your left to right, the first one's on the second one, and the second one is on the third one. I said that right. If I count from your right to left, the first one would be on the 3rd carbon, and the second one would be on the 4th carbon. Well, 3,4 is higher than 2,3, so 2,3 wins. So I'm going to say 2,3 dimethyl. Going backwards, I see 2 1 carbon side chains. Where are they? On the 2nd carbon and on the 3rd carbon. And what do they exist on? A 5 carbon single bonded parent chain. Just going backwards. I can go from name now to structure to name, going backwards and forwards. It's why these rules are what they are. Okay. So here I got 3-methyl hexane. I'm going to start right with that hexane and get my parent chain straightened out. 6 carbons, single bonded. No, I don't like this picture necessarily, but we're going to roll with it. I redid all the next ones, so the next ones are going to be pretty good. All right, I have a 1 carbon side chain methyl. Where do I put it? On the 3rd carbon. So that goes there. Fill in my H's. And this is going to look a lot like the first one we did. C7, H16, all single bonded, it's saturated. So 2-methylbutane and 3-methylhexane are very similar. Notice the butane just had a 4-carbon main chain. Hexane has a 6-carbon main chain. Where did I put the methyl? In this case, the 3rd carbon. On the first example we did, we put it on the 2nd carbon. Okay. Now things are going to get fun because I have ynes, so I have to deal with those. So hex, looking it right up, I hex yne. I have 6 carbons as my hex. Then I look up yne. Yne on table Q tells me that there has to be a triple bond. Well, where do I put the triple bond? I put it on the 2nd carbon. So notice that that 2 in front of the hex yne, so that 2 goes with hexyne. Hexyne, where's the difference from what the base should be, which is hexane? It's in the yne. So the 2 is referring to the deviation, which is this triple bond. It's telling me to put the triple bond on the 2nd carbon. So let's do that. So there's my 6 carbons with a triple bond now on the 2nd carbon. Then I have to deal with this methyl. YL tells me it's a side chain. The side chain is 1 carbon long. And then where am I going to put it? On the 4th carbon. So on the 4th carbon, put a methyl group. So we did that. Then guess what we do? Fill in the H's and we're done. But here's where you need to be careful, because as you put these H's in, each carbon can only have 4 bonds. And if you look closely at where the triple bond is, the carbon to the left of the triple bond has 4 dashes around it. And the carbon on the right-hand side of the triple bond has 4 dashes around it. So if a carbon already has 4 bonds, you can't give it any hydrogen. And then triple bond means that the generic formula would be CnH2n minus 2. So 7 times 2 is 14, minus 2 is 12. Boom, and it fits. So it does match. That if there's a triple bond present, I can only put 12 hydrogens on 7 carbons. Therefore, it is unsaturated because there are open parking spots. This thing could hold more hydrogens. If I broke that triple bond, I could get a lot more hydrogen in there. Good? All right, let's go let's do the other way. Let's go from the picture to the name. So either way I count this, I get 4 carbons. This is a great example. So if I go around the corner, I get 4 carbons, or if I go straight, I get 4 carbons. And here's where I have to pick the straight, because the straight would have a double bond in it. So you see what I mean by double bond trumps. So I know it's a butte right off the bat. 4 carbons is butte. I got to figure out the root based on the bonding. Well, there's a double bond present in the side chain. I'm sorry, I misspoke. There's a double bond present in the main chain, because we just said that the main chain would always have the double bond. I'm doing a lot of misspeaking, so I hope that hope you can keep it straight. I'm trying to correct myself right away. I guess I haven't had enough coffee. Maybe I've had too much. The double bond is on the 1st carbon. So if I count from left to right, it's after the 1st carbon. If I count from right to left, it's after the 3rd carbon. 1 trumps. So here's the other rule there. Once I realize that I count from left to right, now for this whole molecule, I count for left to right. I count left to right to give that double bond on the lowest carbon. And when I do that, now I have to continue counting left to right to figure out where the methyl goes. Does that make sense? Once I count left to right, I count left to right. If the molecule dictates that I have to count right to left, then for the rest of the naming structure, I count right to left. Okay? So I have a 1 carbon side chain. That's a meth. Meth ending with a YL, it becomes methyl. I take the ane, make methane, and make it methyl. Then where did I put that? Well, counting from left to right, it's on the 2nd carbon. So it's 2-methyl, 1-butene is the correct way. And you do need the 1, you do need the 2. Count them all up. I got C5H10. It's unsaturated because I have a double bond. All right, next one. 1, 2, 3, 4, 5 carbons. 5 carbons is one we're good at. I pent. That's one I know instinctually. But then I see a triple bond present. So I have to find the triple bond in the picture. Find the triple bond in the picture that ends in "-ine". So this is going to be pentyne. Now, where do I put that? If I count from left to right, the triple bond is on the 2nd carbon. If I count from right to left, it's on the 3rd carbon. 2 is lower than 3, pick 2. This is just 2-pentyne. No side chain, easy. Review of single and triple bonds. Good. Now here comes the big bad daddy. I'm gonna I'm going to start with oct. Now, I used to have to hand draw this, but not anymore. It's animated and it's not a lot of room, so be careful how you write this because you can write this somewhere else on the page if there's not enough room in the little uh, rectangle that I gave you to write in it. But I need to get 8 carbons in there. So there's 8 carbons. Bam. Okay. Then I have this to deal with. I have an ene, and an ene means, so look up the word with an ene, notice it has a double bond. So I need to put a double bond somewhere in this chain. Where? Well, first of all, there's 2 double bonds. It's a diene. That di comes right in front of the ene if there's 2 double bonds. Where am I going to put them? We'll put them on the 2nd carbon and put them on the 5th carbon. Okay, one on the 2nd, one on the 5th. So I'm just going to do that. I'm going to put 1 double bond on the 2nd carbon and 1 double bond after the 5th carbon. Done. Now I have to attack the side chain. I have a methyl. So again, 1 carbon, methyl, 1 carbon. We're going to see lots of methyls and ethyls. You won't see a lot of propyls and butyls much because it's got to be a huge parent chain to get 4 carbons as just a side chain. You got to have a ton of carbons on either side to make the 4 small enough to be a side chain, right? We're going to see a lot of methyls and ethyls. So I have a 1 carbon side chain. Where am I going to put that 1 carbon side chain? Put it on the 4th carbon. So count over again from left to right. When you're drawing them, from the words, I would always count left to right. Just make it simple. Could you count from right to left? Sure. But then you'd have to consistently count from right to left for that whole molecule. Okay. So there I'm going to put my methyl, which is another carbon, onto the 4th carbon in the main chain. And then I'm almost done. All I got to do is fill in some hydrogens. And I do that by counting and make sure I put them all in the right places where there are, single bonds need extras than double bonds. And you can look carefully at this particular example. There are 3 hydrogens that can go either way. I put them all on the bottom just to make drawing it in nice. But if you look at the first double bond, the carbon that is on, or the double bond that's on the carbon number 2, the hydrogens I both put on the bottom side. You could have put them both on the top side. You could have put one up and one down. Because there's that methyl there, I try to put at least the one that's directly below the methyl on either side facing down, just because it's easier to draw that way. I could have on both double bonds put all of them down. You notice I did start with the first one up. I could have put that one down also. There is no rhyme or reason to that. When we get into the modeling kits, you'll see it can go up or down. You can see that these carbon straight chains, the way they bond, there actually is a little bit of a rigidness to it. And if you Google some of these guys, you'll see some different drawing rules where a lot of times you can literally just draw the lines, and where each corner is considered a carbon. Or they'll draw it with a C there and then not draw the hydrogens and just assume that they're all there. So there's a lot of different ways to draw these. And hence there's a lot of different correct ways to draw this. As long as those hydrogens are all on the right carbons and each carbon has 4 bonds, it really is the same thing is what I'm trying to get at. So all the hydrogens that I put on the bottom that are next to that double bond could be facing up. The ones that are on single bonds have to be facing down because there's one up and down. Okay, does that make sense? Because we got to get 4 bonds around each carbon. With that, count them all up. I have 9 carbons, I have 16 hydrogens, and because there are double bonds present, it is unsaturated. Do notice, though, there are 2 double bonds. So when there's 2 double bonds, the generic formula for alkenes does no longer work. That only works when there's 1 double bond. When there's 1 double bond, the generic formula works perfect. When I start getting into 2 double bonds or 2 triple bonds, that formula goes out the window. And if by chance you make something silly and complex with like a triple bond and a double bond, well, then it's really not going to work. Okay. But guess what? Sorry it took so long, but we are donezo. So, side chains, practice. Let's get to it.